Can time flow backward? You're holding a coffee cup. Your fingers loosen, and it slips. In the fraction of a second before it hits the floor, you know what's about to happen. The ceramic strikes the tile with a sharp crack, and suddenly what was whole becomes a scattered puzzle of broken pieces, dark liquid spreading across the floor in an expanding pool. We've all seen this happen. We've all experienced that sinking feeling as something precious shatters. But here's a question that might seem absurd at first. Why don't we ever see the reverse? Why don't shattered pieces spontaneously leap up from the floor, reassemble themselves midair, and land perfectly intact in your hand, the coffee neatly contained once more? Your immediate answer might be, because that's impossible. Because that's not how the world works. And you'd be right. But here's the thing that puzzled physicists for more than a century. The fundamental laws of physics that govern those ceramic molecules don't actually forbid the cup from unbreaking. The equations of motion that describe how particles move work equally well whether time flows forward or backward. At the deepest level, we understand the universe doesn't have a preference for which direction time moves. And yet, cups break. Cream mixes into coffee and never spontaneously unmixes. Ice melts. Buildings crumble. Stars burn out. Every single thing you've ever witnessed moves in one direction through time, from order toward disorder, from past toward future, never the reverse. Tonight, we're going to explore one of the deepest mysteries in all of physics: why time has an arrow, why the universe distinguishes between past and future when its fundamental laws do not. We'll visit the quantum realm where particles briefly violate time's flow. We'll contemplate the disturbing possibility that you might be a random brain floating in space with false memories. We'll ask whether gravity could reverse time's direction. And we'll explore the mystery of consciousness itself and why you remember yesterday but not tomorrow. This is a journey into entropy, into the architecture of time itself. And let's discover together why time flows forward, why eggs never unbreak, and what it all means for our place in this strange, asymmetric universe. The story begins in the middle of the 19th century, with steam engines and the scientists who tried to understand them. The Second Law of Thermodynamics. In the 1850 seconds, a German physicist named Rudolf Clausius was thinking hard about heat. This might not sound like the most exciting topic, but what Clausius discovered would eventually reshape our understanding of time itself. He was trying to answer a practical question. When you burn coal to heat water and make steam, where does the energy go? Can you ever get it all back? Can processes perfectly reverse themselves? The context matters here. The Industrial Revolution was in full swing. Steam engines powered factories, trains, ships. Engineers wanted to build better engines, more efficient ones. But there was a puzzle. When you burn coal, you release energy. Some of that energy does useful work, turning wheels and pistons. But much of it seems to disappear, dissipated as waste heat. Why? And more importantly, is there a fundamental limit to how efficient an engine can be? A French engineer named Sadi Carnot had tackled this question in 1824, decades before Clausius. Carnot imagined an idealized engine operating in a special, reversible way, moving heat between a hot reservoir and a cold reservoir. He proved that no real engine could be more efficient than this idealized Carnot engine, and that the efficiency depended only on the temperatures of the hot and cold reservoirs. Carnot's work was brilliant, but it was based on an incorrect theory of heat, called the caloric theory, which treated heat as a fluid that flowed between objects. It took decades for physicists to realize that heat is actually the random motion of particles, not a conserved fluid. Through careful mathematical reasoning, Clausius arrived at a remarkable conclusion. He introduced a new concept, a quantity he called entropy, from the Greek word for transformation. And he stated, what would become known as the Second Law of Thermodynamics. In any isolated system, entropy can never decrease. It can stay the same, or it can increase, but it cannot go down. Clausius defined entropy in a very specific way. For a reversible process, the change in entropy equals the heat transferred divided by the temperature at which the transfer occurs. This mathematical definition seemed abstract, but it captured something profound about the directionality of natural processes. But what is entropy? Really, the word gets thrown around a lot, often vaguely described as disorder or chaos. And while that's not entirely wrong, it misses the profound precision of what entropy actually measures. Let's dig deeper, because understanding entropy properly is the key to understanding time's arrow. Imagine you have a box divided into two halves by a partition. In one half, you have 100 gas molecules, all bouncing around. The other half is empty, a vacuum. Now imagine you remove the partition. What happens? The gas expands to fill the entire box. The molecules spread out. They don't all stay huddled in one half. Here's the key insight. There are many, many more ways for those 100 molecules to be spread throughout the entire box than there are ways for them to all be in just one half. If you could somehow track every individual molecule and count every possible arrangement, the number of arrangements with molecules everywhere vastly outnumbers the arrangements with molecules only on one side. Let's make this more concrete with actual numbers. With 100 molecules in a box of a given size, there's essentially one way for all the molecules to be in the left half. They all have to have positions in the left side of the box, but there are approximately 2 to the 100th power ways for the molecules to be distributed throughout the entire box, giving you 2 choices for each of 100 molecules. That's about 10 to the 30th power different arrangements. 10 to the 30th power. That's a million, trillion, trillion. The ratio is so overwhelming that if you removed the partition, you'd wait longer than the age of the universe for the molecules to randomly all end up back in one half. Entropy, in its most precise definition, measures the number of microscopic arrangements that correspond to the same macroscopic state. A state with high entropy has many possible microscopic configurations. A state with low entropy has relatively few. When the gas spreads out, it moves from a low entropy state, many molecules in half the space, few possible arrangements, to a high entropy state, molecules anywhere in the box, enormously many possible arrangements. Think about your bedroom. When it's clean, everything is in its place. Books on the shelf, clothes in the closet, desk organized. There are relatively few arrangements that count as clean. But there are countless ways for the room to be messy. Books could be on the floor, on the bed, under the desk. Clothes could be scattered anywhere. Each different messy configuration is distinct, and there are vastly more messy states than clean states. This is why rooms tend to get messy if you don't actively maintain them. It's not that there's a force pulling toward messiness. It's that random disturbances, you dropping things, walking around, moving objects, tend to push the system toward states that are more numerous, and messy states vastly outnumber clean states. The second law says, systems evolve toward states that have more possible arrangements. They evolve toward higher entropy, and this makes intuitive sense once you think about it in terms of probability. If there are 1 billion ways to be spread out and only one way to all be in the corner, random motion is overwhelmingly likely to lead toward being spread out. Ludwig Boltzmann, working in the late 19th century, made this mathematical and precise. He showed that entropy is related to probability. The formula is elegant. Entropy equals a constant, now called Boltzmann's constant, times the natural logarithm of the number of microstates. More possible arrangements means higher entropy. Fewer possible arrangements means lower entropy. Boltzmann's insight was revolutionary. He connected the macroscopic property of entropy with the microscopic world of atoms and molecules. At the time, atoms were still controversial. Not all scientists accepted that matter was made of discrete particles. But Boltzmann showed that if you assumed atoms existed and obeyed mechanical laws, you could derive the second law of thermodynamics statistically. Here's what makes this revolutionary. The second law isn't like other laws of physics. It's not absolute. It's statistical. It's about overwhelming probability, not impossibility. Those 100 gas molecules could, in principle, all randomly bounce back into one half of the box. Let's think about what inconceivably unlikely really means. If you waited for all 100 molecules to randomly congregate in one half, you might wait for a time longer than the age of the universe and never see it happen. With a realistic number of molecules, say, a mole of gas, which contains about 600 billion trillion molecules, the probability of spontaneous compression becomes so small that it's effectively impossible. We're talking about probabilities like 1 divided by 10 to the power of 10 to the 23rd. That's not just a big exponent. That's an exponent that's itself a huge number. The probability is so small that there aren't enough particles in the observable universe, or seconds since the Big Bang, to even count that high. This statistical nature puzzled physicists for decades. How can a fundamental law be merely statistical? But Boltzmann showed this is exactly right. With a very large number of particles, the statistical becomes effectively certain. The larger the system, the more overwhelming the probability that entropy will increase, and the less likely you'll ever see a spontaneous decrease. Boltzmann faced fierce criticism during his lifetime. Some physicists thought his statistical approach was flawed or incomplete. Others rejected the atomic theory that underlies it. The debates became intense, and Boltzmann, who struggled with depression, found the opposition deeply troubling. Tragically, he died by suicide in 1906, before the final vindication of his ideas through the confirmation of atomic theory. Today, we recognize Boltzmann as one of the giants of physics. His tombstone in Vienna bears his entropy formula, S equals K log W. It's a fitting tribute to a man who showed that the disorder we see in nature is actually exquisite order when viewed through the lens of probability and statistics. Let's make this concrete with something you've experienced countless times. Mixing cream into coffee. You pour the cream in, and it swirls through the dark liquid in beautiful, turbulent patterns. Watch it closely. The cream forms tendrils, spirals, marbled veins of white against brown. For a moment, you can see the boundary between cream and coffee, the interface where they meet. But within seconds, the two liquids blend into a uniform tan color. The cream molecules spread throughout the coffee. The distinct regions disappear. What was separated becomes mixed. Entropy increases. The process is fascinating at a molecular level. Each cream molecule is in constant thermal motion, jiggling and bouncing. The coffee molecules are doing the same. At the boundary, cream molecules bounce into regions occupied by coffee molecules. Coffee molecules bounce into regions occupied by cream. With each collision, with each random jiggle, the two populations intermingle more thoroughly. There's no force pulling cream and coffee together, no attraction making them mix. It's purely random motion. But that random motion, acting on trillions upon trillions of molecules, creates a definite direction, from separated toward mixed, from low entropy toward high entropy. Now imagine trying to reverse this. You'd need every single cream molecule to spontaneously migrate back together, separating perfectly from the coffee molecules until you had pure cream floating on top of pure coffee again. Is this forbidden by the laws of physics? No. Each molecule is simply bouncing around randomly. In principle, They could all randomly bounce in just the right way to segregate. In practice, the number of arrangements corresponding to mixed so vastly outnumbers the arrangements corresponding to separated that you will never, ever see it happen. Think about the numbers. A cup of coffee might contain something like 10 to the 25th molecules. Each molecule has a position and a velocity. The space of possible arrangements is incomprehensibly vast. Within that space, the region corresponding to cream and coffee separated is infinitesimally tiny compared to the region corresponding to cream and coffee mixed. If you could sample random configurations from this space at the rate of 1 per second, and you could do this for the entire age of the universe, you still wouldn't have a chance of finding a separated configuration starting from a mixed one. The probability isn't just small, it's small beyond small. Small in a way that makes impossible seem like an appropriate word, even though technically the probability is non-zero. The second law explains why ice melts in warm water, but warm water never spontaneously freezes into ice while heating up the surrounding air. It explains why perfume disperses through a room instead of all flowing back into the bottle. It explains why your bedroom gets messy if you don't clean it, not neater. It explains the universal human experience of order degrading into disorder. But here's where things get truly strange. Clausius and Boltzmann were describing something that seems to be fundamentally asymmetric in time. Entropy increases toward the future. It doesn't increase toward the past. If you watch a video of cream mixing into coffee, you can instantly tell if it's playing forward or backward. The forward direction shows mixing. The backward direction shows the impossible. This is peculiar because, as we'll explore in detail, the underlying equations that describe molecular motion don't care about time's direction. Newton's laws of motion work the same whether time flows forward or backward. If you film billiard balls colliding and play it in reverse, you can't tell the difference. The physics is time-symmetric. Yet somehow, when you have many particles, this asymmetry emerges. Entropy gives us an arrow, a direction, and it points relentlessly forward. But wait, why does entropy increase specifically toward what we call the future? Couldn't it increase toward the past instead? What determines which direction is which? This question leads us to an even deeper mystery, one that a brilliant astrophysicist would articulate with unusual clarity in 1928. Arthur Eddington and Time's Arrow. Arthur Stanley Eddington was one of the great scientists of the early 20th century. He helped prove Einstein's theory of general relativity through observations of starlight bending during a solar eclipse. He understood the nuclear processes that power the sun. He was deeply philosophical about physics, always probing the meaning behind the mathematics. In 1928, Eddington published a book called The Nature of the Physical World, and in it, he introduced a metaphor that would become central to how we think about time. He called it the arrow of time. Here's how he described it. Let us draw an arrow arbitrarily. If as we follow the arrow we find more and more of the random element in the state of the world, then the arrow is pointing towards the future. If the random element decreases, the arrow points towards the past. Read that again, slowly. Eddington is saying something profound. We can define which direction is the future by watching which direction entropy increases. The arrow of time and the arrow of entropy are the same thing. He also wrote something that shows just how seriously he took the second law. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, but if your theory is found to be against the second law of thermodynamics, I can give you no hope. That's quite a statement. Above even the foundational equations of electromagnetism, above experimental results, Eddington places the second law. Why? because it defines the very direction of time itself. Think about what this means. Past and future aren't just labels we arbitrarily assign. They correspond to something physical. The direction of entropy increase. The past is the direction of lower entropy. The future is the direction of higher entropy. Time has an orientation, a directionality, an arrow. This arrow manifests in countless ways. Broken glass doesn't reassemble. Ashes don't spontaneously unburn into logs. Dead organisms don't reanimate. Memories form only of the past, never of the future. Causes precede effects. But here's the puzzle that kept physicists awake at night. Why does the arrow point the way it does? Why did the universe start in a low entropy state such that entropy could increase? Why wasn't the universe always at maximum entropy, in thermal equilibrium, with no arrow at all? Consider the full implications. If the universe had started at maximum entropy, in perfect equilibrium, nothing interesting would ever happen. No stars, no planets, no life, no you. Everything would just sit there, static and boring, for eternity. The fact that you exist, that you're listening to these words, that there are complex structures in the universe at all, depends crucially on the fact that the universe began in a very special, very low entropy state. We'll come back to this mystery later. For now, the key insight is this. Eddington showed us that entropy and time are deeply connected. The second law doesn't just describe how things change over time. It defines what we mean by time's direction in the first place. And yet, we still face a troubling paradox. At the microscopic level, the level of individual particles following deterministic laws, there is no arrow. The equations work equally well in both directions. So where does the macroscopic arrow come from? How does time-symmetric physics give rise to time-asymmetric thermodynamics? Before we tackle that puzzle, let's make the second law even more concrete by exploring the most famous example of irreversibility, the breaking egg, and why it never, ever unbreaks. Why eggs don't unbreak? Let's get specific. Take a raw egg in its shell, held at arm's length above a tile floor. Release it. Gravity accelerates it downward at 9.8 meters per second squared. It falls for perhaps half a second. Then impact. From the 2022 of the Life 2, the shell cracks, the membrane ruptures, yolk and white spill out in a spreading puddle. Mixing together, the proteins beginning to denature from the force of impact. Within moments, you have a mess on the floor that bears little resemblance to the structured object you were holding. Now, here's the question that should seem almost absurd. Why don't the yolk and white spontaneously unmix, flow back together, push themselves back inside a reforming shell, and leap up into your hand? You know instinctively this is ridiculous. But let's be precise about why. After all, every single molecule in that broken egg is following the laws of physics. None of those laws say, "Thou shalt not unbreak." The molecules in the yolk could, in principle, all move in exactly the right way to reverse the process. The laws of motion are time reversible. The answer comes down to numbers. Not just large numbers, but incomprehensibly vast numbers that dwarf anything in ordinary experience. That egg contains something on the order of 10 to the 24th power molecules. Each one is bouncing around, colliding with others, following Newton's laws of motion. At any given instant, there are an enormous number of possible arrangements of all those molecules. When the egg is intact, the molecules are constrained. The shell holds them in a specific geometry. The yolk is separated from the white by a membrane. This represents a relatively low entropy state, not because it's ordered in some vague sense, but because relatively few arrangements of all those molecules correspond to intact egg. When the egg breaks, all those constraints vanish. The molecules can be anywhere on the floor. The yolk and white can mix in any pattern. The number of possible arrangements explodes. The entropy skyrockets. To reverse this, you'd need an incredibly specific sequence of events. Every single molecule would need to move in exactly the right direction, at exactly the right time. The probability of this happening by random thermal motion is approximately 1 over a number so large it makes the number of atoms in the observable universe look tiny. Let's try to get our heads around just how unlikely we're talking about. Imagine you could check every second to see if the egg has unbroken. And imagine you could do this for the entire age of the universe, about 13.8 billion years. That's about 4 times 10 to the 17th power seconds. The probability of the egg spontaneously unbreaking in any given second is something like 1 over 10 to the power of 10 to the 24th. That's not 10 to the 24th. That's 10 to the power of a number that's already a trillion. The probability is so small, it doesn't even make sense to write it out. You could wait for a time that makes the age of the universe look like a single heartbeat, and you still wouldn't see it. You could wait for 10 to the 100th universes worth of time, and you still wouldn't see it. The probability is that infinitesimally small. This is the power of the second law when applied to macroscopic systems. It's not that reversal is impossible. It's that it's so overwhelmingly improbable that it might as well be impossible. The same logic applies to every irreversible process you've ever witnessed. Wood burns to ash and gases, and the number of arrangements of all those molecules is vastly greater when spread out than when organized into cellulose and lignin. Glass shatters, and the shards can land in countless different configurations, all corresponding to higher entropy than the intact glass. Ice melts, and the water molecules can arrange themselves in liquid form in many more ways than in the rigid structure of ice. Entropy increase is just another way of saying systems evolve towards states that have more possible microscopic configurations. And because there are so many more high entropy configurations than low entropy ones, the direction is essentially one way. This is also why the second law is fundamentally about initial conditions and boundary conditions, not about the equations of motion themselves. Given any microscopic configuration, if you reversed all the velocities of all the particles, the system would evolve backward. The broken egg would unbreak. The mixed cream would unmix from the coffee. But finding a configuration with all the velocities precisely reversed is itself wildly improbable. The space of possible states is dominated by high entropy configurations that, when evolved forward in time, go to even higher entropy configurations. The special low entropy configurations that would evolve backward toward lower entropy occupy a tiny, negligible fraction of the total space. Here's another way to think about it. Imagine you have a video of the egg breaking. If you watch it forward, it looks normal. If you play it backward, it looks absurd, impossible, magical. Why? Because your brain, trained by a lifetime of experience, knows the direction of entropy increase. You know what's probable and what isn't. But if you had a video at the molecular level showing just a few molecules colliding, you couldn't tell if it was playing forward or backward. The microscopic dynamics are time-symmetric. It's only when you zoom out, when you have many molecules, when statistical ensembles dominate, that the arrow emerges. This emergence of irreversibility from reversible dynamics puzzled physicists deeply. How can many time-symmetric processes combine to create time asymmetry? The answer, as Boltzmann showed, is that it's not about individual trajectories. It's about the space of all possible trajectories and the overwhelming bias towards certain regions of that space. We live in a universe where the initial conditions were such that entropy was low. From that low entropy starting point, the statistics take over, and evolution toward higher entropy becomes essentially certain. But this raises the question, Why were the initial conditions low entropy? Why did the universe start in a special state? We'll grapple with that profound mystery later. For now, we've established why eggs don't unbreak. Because there are so many more ways to be broken than to be whole, and random processes explore the space of possibilities in a way that overwhelmingly favors higher entropy. Yet the puzzle deepens when we look closely at the microscopic world itself. Because there, we find something surprising: perfect time symmetry, or nearly so. Let's explore that strange landscape, the microscopic world's symmetry. Isaac Newton's laws of motion, formulated in the late 17th century, have a remarkable property. They are time reversible. If you have a solution to Newton's equations describing how a system evolves forward in time, you can reverse all the velocities, and you get a perfectly valid solution describing the system evolving backward. Imagine two billiard balls colliding on a pool table. Ball A rolls toward ball B. They strike. Ball A slows down and veers left. Ball B shoots off to the right. Now imagine you filmed this and played the video backward. You'd see ball B rolling in from the right, ball A rolling in from the left. They collide, and ball A speeds up and rolls away. Is this backward video physically possible? Absolutely. There's nothing in Newton's laws that forbids it. If the balls had exactly the right velocities and spins, the collision would proceed exactly as shown in the backward video. The laws of motion don't distinguish between forward and backward in time. This time reversal symmetry holds for all of classical mechanics. Planets orbiting stars, pendulums swinging, springs oscillating, waves propagating, all of these are described by equations that work equally well if you replace time t with negative time dot t. When quantum mechanics came along in the early 20th century, physicists found that the Schrödinger equation, which governs how quantum states evolve, is also time reversible. The fundamental dynamics of quantum systems don't have an arrow. Even Einstein's general relativity, which describes gravity as the curvature of space-time, has solutions that work both forward and backward in time. A star collapsing into a black hole can be time reversed to give a white hole that spews matter out mathematically valid, even if we never see white holes in nature. So here's the paradox in full force. The microscopic laws are time-symmetric, but the macroscopic world is manifestly time-asymmetric. How does this asymmetry emerge? How do you get an arrow of time from laws that have no arrow? This puzzle has a name. In 1876, a scientist named Joseph Loschmidt raised what's now called Loschmidt's paradox. He pointed out that if you have a system of gas molecules evolving toward equilibrium, increasing entropy as they spread out, you could in principle reverse all their velocities at any moment. Then the system would evolve backward, decreasing entropy, returning to its initial state. Since the reversed velocity state is just as valid a solution to the equations as the original state, how can you say entropy always increases? Boltzmann's answer was subtle and profound. He said entropy doesn't always increase for every possible state. What's true is that entropy increase is typical. The space of all possible microscopic states is dominated by states that, when evolved forward, go to higher entropy. States that evolve toward lower entropy exist, but they occupy a vanishingly tiny fraction of the total space. If you prepare a gas in a low entropy state, all molecules in one corner, could you reverse all the velocities halfway through and watch it contract back? Yes, in principle. But that reversed velocity state is incredibly special, incredibly fine-tuned. The odds of randomly being in such a state are astronomically small. Here's an analogy. Imagine you have a large jar filled with sand, half black and half white, carefully separated with the black on one side and white on the other. You shake the jar. The sands mix. Entropy increases. Could you shake it in exactly the right way to unmix them? In principle, yes. In practice, you'd need to control every grain with impossible precision. Random shaking will never unmix them. The second law emerges not from the fundamental laws forbidding entropy decrease, but from the statistical structure of the space of possible states. High entropy states vastly outnumber low entropy states. Random evolution explores this space and overwhelmingly tends toward the more numerous regions. There's another famous paradox called the Poincaré recurrence theorem. Henri Poincaré proved that any finite system with finite energy will, if you wait long enough, eventually return arbitrarily close to its initial state. So if you have gas molecules that spread out from one corner to fill a box, eventually, after an unfathomably long time, they'll all end up back in the corner again. Doesn't this contradict the second law? No, because the recurrence time is so long it's meaningless. For a macroscopic system, the Poincaré recurrence time is longer than any physically meaningful timescale. The age of the universe is nothing compared to how long you'd have to wait for significant entropy decrease through recurrence. Boltzmann understood all this. He showed that the second law is compatible with time-symmetric microscopic dynamics because it's a statistical law about typical behavior, not an absolute law about every possible trajectory. But this raises a deep question about our place in time. We find ourselves in a relatively low entropy state. The universe around us is full of structure, stars, galaxies, planets, life. Entropy is not at maximum. We're in the middle of the arrow, watching entropy increase. Why? Why aren't we at equilibrium, with maximum entropy, where nothing interesting happens? Boltzmann's answer: because we couldn't exist at equilibrium. Life requires entropy gradients. Thought requires low entropy structure. We observe a low entropy universe for the same reason fish observe a wet universe. That's the only kind where we can exist. This is a kind of anthropic reasoning, a selection effect. But it doesn't fully explain why the universe as a whole has a low entropy past. We'll return to that mystery. For now, the key point is this: microscopic physics is time-symmetric, or nearly so. But macroscopic physics has a profound asymmetry that emerges from statistics and initial conditions. Actually, I said nearly so because there's one place where time symmetry breaks down even at the fundamental level. In the strange world of particle physics, there's a subtle violation of time reversal symmetry. It's small, it's rare, and it has nothing to do with everyday thermodynamics. But it's real, and it's fascinating. Let's explore it. CPT symmetry. When particles dance backward. In the quantum world of subatomic particles, physicists have discovered several fundamental symmetries. These symmetries are transformations you can apply to a physical system that leave the laws of physics unchanged. Three of the most important are called C, P, and T. C stands for charge conjugation. This means replacing every particle with its antiparticle. An electron becomes a positron, a proton becomes an antiproton, and so on. Antiparticles have the opposite electric charge but otherwise identical properties. P stands for parity. This means flipping space, creating a mirror image. Left becomes right, right becomes left. It's like looking at the universe in a mirror. T stands for time reversal. This means running the clock backward, replacing future with past and past with future. For a long time, physicists assumed each of these symmetries held individually. The laws of physics, they thought, don't care if you swap particles for antiparticles, don't care if you mirror everything, and don't care if you reverse time. Then came the shocking discoveries of the 1,950 seconds and 1,960 seconds. In 1956, two Chinese-American physicists, Sung-Dao Lee and Chen-Ning Yang, proposed that parity might be violated in the weak nuclear force, the force responsible for certain types of radioactive decay. This was tested in 1957 by Qian-Xiang Wu in an elegant experiment involving cobalt-60 atoms. She cooled the cobalt atoms to near absolute zero and aligned their spins using a magnetic field. Then she watched which direction the electrons were emitted during beta decay. If parity were conserved, electrons should be emitted equally in all directions. They weren't. There was a preference. The weak force violates parity symmetry. This was stunning. Nature distinguishes between left and right at a fundamental level. If you watch certain particle decays in a mirror, you'd see something that doesn't actually happen in our universe. Physicists quickly realized that charge conjugation is also violated. The weak force treats particles and antiparticles differently, but they proposed a new combined symmetry, CP. Maybe if you both flip space and swap particles for antiparticles, that combined operation is a symmetry. For a few years, this seemed right. Until 1964. James Cronin and Val Fitch, working with colleagues at Brookhaven National Laboratory, studied the decay of particles called neutral kaons. These strange particles can transform into their own antiparticles. Cronin and Fitch discovered that the decay patterns violated CP symmetry. Even the combined operation of swapping particles for antiparticles and flipping space wasn't a perfect symmetry. This was extraordinary. It suggested that at the most fundamental level, nature distinguishes between different directions and different types of particles in subtle but definite ways. Now, there's a beautiful mathematical theorem in quantum field theory called the CPT theorem. It says that if you apply all three operations together, charge conjugation, parity flip, and time reversal, the combined CPT symmetry must hold for any reasonable quantum field theory. It's not a choice. It's a consequence of very basic assumptions about how quantum fields work in relativistic spacetime. So if CP is violated, then by the CPT theorem, T must also be violated in exactly the compensating way. This was confirmed directly in experiments in 1998. Physicists observed that certain particle decay processes happen at different rates depending on whether you're running time forward or backward. Time reversal symmetry at the level of fundamental particle interactions is broken. Let's be clear about what this means. It doesn't mean macroscopic objects can evolve backward in time. It means that certain very specific quantum processes involving the weak nuclear force have a slight preference for one time direction over the other. For example, a particular type of kaon decay might happen with probability 0.5, 1 inches the forward direction, and probability 0.49 inches the time reverse direction. It's a small effect, but it's real and measurable. Why does this happen? It comes down to the structure of the weak force and how quarks interact. The details involve complex mathematics about the mixing of different quark types, but the upshot is clear. The weak nuclear force genuinely violates time reversal symmetry. Is this the origin of the thermodynamic arrow of time? No. The effect is far too small and far too specialized. It only shows up in rare particle decays. It has nothing to do with why coffee mixes or eggs break. The thermodynamic arrow emerges from statistics and initial conditions, not from fundamental time asymmetric forces. However, this fundamental CP violation does have profound cosmological implications. In the early universe, if all processes were perfectly symmetric between matter and antimatter, they should have annihilated each other completely, leaving only photons. The slight CP violation allowed a tiny excess of matter to survive. That tiny excess is everything we see. All the stars, planets, and galaxies are made from the leftover matter that didn't annihilate. So while fundamental time reversal violation doesn't explain everyday arrows of time, it may explain why there's matter around for those arrows to apply to. The CPT theorem itself is fascinating. It tells us that if you create an anti-universe made of antimatter, mirror-flipped, running backward in time, that universe would obey exactly the same laws of physics as ours. The combined transformation of all three symmetries is sacred, even if each individually can be violated. This brings us to a strange idea. Imagine a universe that's the mirror image of ours, made of antimatter, where time runs backward. From our perspective, that sounds bizarre, but from the perspective of someone in that universe, we would be the bizarre mirror image anti-universe running backward in time. The CPT theorem says these two perspectives are equivalent. There's a deep philosophical point here about the nature of time itself. If the laws of physics are CPT symmetric, then in some sense, there's no absolute distinction between forward and backward. The arrow we experience is a contingent feature of our particular cosmic history, not a feature of the fundamental laws. This connects to the thermodynamic arrow. We say entropy increases toward the future, but someone in a time-reversed universe would say the same thing from their perspective. The future is whichever direction entropy increases. The arrow is defined by the boundary conditions, by how the universe started, not by the dynamics. Yet the dynamics do matter in one small way, thanks to CP violation. The weak force introduces a genuine, if tiny, asymmetry. It's a subtle hint that even at the fundamental level, time has a direction. But let's not get too carried away. The everyday arrow of time, the reason you age, remember the past, and watch ice melt has nothing to do with CP violation. It has everything to do with entropy. And that brings us to one of the strangest ideas in modern physics. An idea that takes Boltzmann's insights to a disturbing extreme. What if the entire ordered universe you see is a random fluctuation? What if you are too? Welcome to the world of Boltzmann brains. Boltzmann brains. Order from chaos. Let's return to Ludwig Boltzmann in the late 19th century. He had explained entropy brilliantly, showing it was about probability and the number of microstates. But he faced a puzzle. If entropy always increases, if the universe is heading toward maximum entropy and thermal equilibrium, why isn't it already there? Why do we see stars, structure, low entropy? Boltzmann proposed a daring idea. Maybe the universe is, on average, at maximum entropy, in thermal equilibrium. An infinite, featureless void. But even at equilibrium, there are random fluctuations. Particles jiggle around randomly. Most of the time, these fluctuations are small and don't create much structure. But very occasionally, over vast timescales, a large fluctuation occurs. A region of space randomly fluctuates into a low entropy state. Our entire observable universe, Boltzmann suggested, might be just such a fluctuation, a rare, enormous departure from equilibrium. We exist in this fluctuation, and we call the direction of increasing entropy the future, because that's the direction the fluctuation is relaxing back toward equilibrium. It's an ingenious idea. It explains why we see low entropy. We're in the middle of a fluctuation. It explains the arrow of time. The fluctuation creates a temporary asymmetry, and it fits with an eternal universe at equilibrium, avoiding thorny questions about how the universe began. But there's a devastating problem with this idea, pointed out by Arthur Eddington in 1931, and later emphasized by physicists like Richard Feynman and Sean Carroll. The problem is this: if our universe is a random fluctuation from equilibrium, then smaller fluctuations are vastly more likely than larger ones. Think about it. The probability of a fluctuation decreases exponentially with its size. A fluctuation that creates just our solar system is far more likely than a fluctuation that creates an entire galaxy. A fluctuation that creates just Earth is far more likely than one that creates the solar system. A fluctuation that creates just a human brain is far more likely than one that creates Earth. In fact, The most likely fluctuation that could produce an observer, someone conscious who thinks they're seeing a structured universe, would be a single brain, popping into existence with fake memories, surrounded by chaos. This is called a Boltzmann brain. It's a disembodied brain that randomly fluctuates into existence in an otherwise featureless void, complete with neural patterns that make it believe it has a past, a body, a life, even though none of that is real. The brain exists for a brief moment before dissipating back into thermal chaos. Here's the disturbing logic. If the Boltzmann fluctuation scenario is correct, then for every real observer, like you, who evolved through billions of years of cosmic history, there are countless Boltzmann brains who think they're you but aren't. They have identical memories, identical thoughts, identical experiences at this moment. But those memories and experiences are illusions created by random chance. And because Boltzmann brains require much smaller fluctuations than real observers, they vastly outnumber real observers. This is not just weird, it's cognitively unstable. If you believe you're a Boltzmann brain, then you can't trust any of your memories or reasoning. The whole edifice collapses. Sean Carroll put it well. The Boltzmann brain argument is a reductio ad absurdum. It's not a serious prediction. It's a way of showing that the Boltzmann fluctuation hypothesis must be wrong. Our universe is not a random fluctuation from an equilibrium background. Something else is going on. What that something else is, we'll explore later. But the key point is this. The Boltzmann brain paradox teaches us that our universe must have a genuinely low entropy past, not just a fluctuation that looks low entropy. If entropy was high in the past and we're a fluctuation, we'd be Boltzmann brains. We're not. So the past really was low entropy. Let's make this even more visceral. Imagine you're a Boltzmann brain, floating in the void. Your neural patterns randomly fluctuate into a state that gives you the experience of reading these words. You seem to remember your childhood, your life, yesterday. But it's all false. You popped into existence a moment ago. There was no yesterday. There's no room around you. You're just a brain in space with fake memories. Can you prove you're not? Well, you could look for evidence of the external world. You could turn your head, see your surroundings, interact with objects. But a Boltzmann brain might also fluctuate into a state where it seems to perceive all that, where its sensory patterns match what it would expect to perceive if the world were real, even though it's all hallucination. The real argument against being a Boltzmann brain is statistical. If the universe has a low entropy past, then evolved brains like yours vastly outnumber Boltzmann brains, because the low entropy past allows for stars, planets, life, evolution. But if the universe is an eternal equilibrium with fluctuations, Boltzmann brains dominate. So which is it? The evidence points strongly to a low entropy past. The cosmic microwave background radiation, the expansion of the universe, the distribution of galaxies, all of this is consistent with a Big Bang, about 13.8 billion years ago, where the universe began in an extraordinarily low entropy state, not a fluctuation, but a genuine beginning. This raises the ultimate question. But the alternative that we're Boltzmann brains is so problematic that we're forced to accept the mystery of the low entropy beginning. The Boltzmann brain paradox also highlights something important about the arrow of time. The arrow is not eternal. It's not a necessary feature of all possible universes. It's a consequence of our particular cosmic history, our particular initial conditions. In an equilibrium universe, there would be no arrow. Time would have no direction. Nothing would change. We live in an interesting epoch, far from equilibrium, riding the arrow of time from the Big Bang toward eventual heat death. And it's only in such an epoch that complex structures like stars, planets, and thinking beings can exist. But we've been talking about thermodynamics and statistical mechanics. What about gravity? Gravity is the force that shapes the cosmos. It creates black holes, regions where space-time itself becomes twisted. Could gravity somehow reverse the arrow of time? Let's explore. Can gravity reverse time? When Albert Einstein published his general theory of relativity in 1915, he revolutionized our understanding of gravity. No longer was it a force pulling objects together. Instead, gravity was revealed as the curvature of space-time itself. Massive objects bend the fabric of space and time, and other objects follow paths through this curved geometry. One of the most remarkable predictions of general relativity is gravitational time dilation. Clocks tick at different rates depending on the strength of the gravitational field they're in. The stronger the gravity, the slower time passes. This isn't just theoretical. It's been measured with exquisite precision. In 1959, physicists Robert Pound and Glenn Rebka used the Mesbauer effect to measure the gravitational redshift of gamma rays traveling between the bottom and top of a 22-meter tower at Harvard. The frequency shift matched Einstein's predictions to within 10%. Later experiments improved this to better than 1%. More dramatically, atomic clocks on GPS satellites in orbit above Earth tick faster than identical clocks on the ground. The difference is only about 38 microseconds per day, but it's significant enough that if GPS didn't account for gravitational time dilation, your navigation would be off by several kilometers within a day. Even more striking, in 2010, physicists at the National Institute of Standards and Technology measured gravitational time dilation over a height difference of just 1 meter. They showed that a clock 1 meter higher ticks faster by about 1 part in 10 to the 16th. Your head ages faster than your feet, if only by a tiny, imperceptible amount. So gravity clearly affects the passage of time. The more intense the gravitational field, the slower time flows relative to regions with weaker gravity. Near a black hole, this effect becomes extreme. If you could hover just outside the event horizon of a massive black hole, time would pass so slowly for you that the entire future history of the distant universe would unfold in what seems like hours to you. But here's the key question. Does gravity reverse time's direction? Does it change the arrow? The answer is no, with important caveats. Gravitational time dilation slows the rate of time, but it doesn't reverse its direction. A clock near a black hole ticks slower, but it still ticks forward. Events still happen in sequence. Entropy still increases locally. The arrow of time still points the same way. Think of it this way. Time dilation is like playing a video at different speeds. Near a massive object, the video plays in slow motion. Far from massive objects, it plays faster. But in both cases, the video is still playing forward. No one is hitting rewind. However, general relativity does allow for some very strange solutions to the equations. Solutions that include closed, time-like curves. These are paths through space-time that loop back on themselves. If you followed such a path, you could potentially travel into your own past. Do these exist in reality? Almost certainly not. They require exotic configurations of matter and energy that we've never seen and that probably violate other physical principles. They're mathematical curiosities more than physical possibilities. And even if they existed, it's not clear they'd truly reverse time's arrow in a thermodynamic sense. There's another gravitational effect worth considering: the expansion of the universe. According to general relativity, space itself can expand, carrying galaxies apart. This expansion creates a kind of cosmological arrow of time. There's a direction in which the universe is larger, and that direction aligns with the thermodynamic arrow. Some cosmologists have speculated about whether the universe could recollapse, entering a contraction phase where space shrinks instead of expanding. If that happened, would the thermodynamic arrow reverse? Would entropy decrease during the contraction? Stephen Hawking once proposed that it might, but he later retracted this idea. The consensus now is that even if the universe recollapses, entropy would continue to increase. The arrow would keep pointing the same way, even as space contracts. The two arrows, cosmological and thermodynamic, wouldn't be tied together in that way. There is, however, a deep connection between gravity and entropy. Black holes have entropy. In fact, they have enormous entropy, proportional to the area of their event horizon. A black hole is, in some sense, the highest entropy object that can fit in a given region of space. When matter falls into a black hole, the entropy of the universe increases dramatically. Jacob Bekenstein and Stephen Hawking developed these ideas in the 1970 seconds, showing that black holes aren't completely black. They emit radiation due to quantum effects near the horizon, radiation now called Hawking radiation. Over timescales much longer than the age of the universe, a black hole will evaporate completely, converting its mass into thermal radiation. This process is profoundly irreversible. The information about what fell into the black hole seems to be lost, scrambled into thermal noise. This raises puzzles about quantum mechanics and information preservation. But for our purposes, the key point is that black holes are entropy engines. They take ordered matter and produce disorder. Gravity, then, contributes to the arrow of time in a subtle way. In the early universe, gravity was working against entropy in a certain sense. Gravity pulled matter together, creating structure, stars, galaxies. This seems like decreasing entropy, creating order. But that's not quite right. The gravitational field itself has entropy. A uniform distribution of matter has lower gravitational entropy than a clumped distribution. When gravity pulls matter into stars and galaxies, the gravitational entropy increases, and this more than compensates for the local decrease in other forms of entropy. The ultimate fate of matter is to fall into black holes, which have maximal entropy. In the very long term, gravity reinforces the thermodynamic arrow, pushing everything toward higher entropy. So can gravity reverse time? No. It can slow time, warp time, curve space-time in intricate ways, but the arrow points forward even in the strongest gravitational fields. Entropy still increases. Causes still precede effects. The arrow of time is more robust than any single force. It's a feature of the universe's initial conditions, playing out through the statistics of countless particles and the geometry of space-time itself. But there's one more arrow we haven't fully explored yet, and it's the most personal one of all. The arrow of your own consciousness. The arrow of memory and experience. Why do you remember the past but not the future? Why does your sense of self flow from yesterday to today to tomorrow? This is the psychological arrow of time, and it's intimately connected to everything we've discussed. Psychological time versus physical time. Close your eyes for a moment and think about yesterday. You can recall events, conversations, meals, thoughts. The memories are there, sometimes vivid, sometimes hazy, but accessible. Maybe you remember breakfast, the taste of coffee, the texture of toast. Maybe you remember a feeling, an emotion that colored your day. Now try to remember tomorrow. You can't. You can imagine tomorrow, anticipate it, plan for it, but you can't remember it. It hasn't happened yet. There's no memory trace in your brain of tomorrow's breakfast, tomorrow's conversations, tomorrow's feelings. The future is blank in a way the past is not. This seems so obvious, it barely needs stating. Of course you remember the past and not the future. But why? At the level of fundamental physics, past and future are nearly symmetric. The equations work both ways. So why does your mind have such a strong asymmetry? Why is the past accessible and the future hidden? This is the psychological arrow of time, sometimes called the epistemic arrow. It's the observation that our knowledge, our memories, our mental states all point toward the past. We have records of what happened before. We don't have records of what will happen next. We can know the past in a way we cannot know the future. Is this arrow separate from the thermodynamic arrow, or are they the same thing? Stephen Hawking argued convincingly that they're intimately related. Memory formation, he pointed out, is a physical process. When you form a memory, neurons in your brain change their configuration. Synapses strengthen or weaken. Chemical patterns alter. Proteins are synthesized. Neurotransmitters are released and reabsorbed. This is a physical change in a physical system, subject to all the laws of physics, including thermodynamics. To change the configuration of neurons requires energy. Your brain uses glucose and oxygen to power its processes. Glucose molecules are broken down through cellular respiration, releasing energy stored in chemical bonds. Some of that energy does useful work, like pumping ions across cell membranes or synthesizing new proteins, but much of it is dissipated as heat. Heat is entropy. So every time you form a memory, you increase the entropy of your brain and its surroundings. The process is thermodynamically irreversible. You can form memories in the direction of increasing entropy. You cannot form them in the direction of decreasing entropy. This isn't a coincidence. It's a deep connection. The psychological arrow and the thermodynamic arrow align because psychological processes are physical processes subject to thermodynamics. Let's dig deeper into what memory actually is. What is a memory, physically? When you remember having breakfast this morning, there's a physical pattern in your neurons that correlates with the physical pattern of breakfast and your surroundings. The toast was crispy, and now there's a pattern of synaptic strengths in your hippocampus and cortex that encodes crispy toast. The coffee was hot, and there's a pattern that encodes hot coffee. Your friend said something funny, and there's a pattern that encodes the words, the tone, the context. Creating this correlation requires that your brain was in a relatively uncorrelated, low-entropy state before the memory formed. Your brain had to have the capacity to record new information. It had to be like a blank page ready to be written on, or more accurately, like a page with some writing that has room for more. As you go through life, experiencing and remembering, your brain's entropy increases. Information accumulates. Correlations multiply. The neural networks that store your memories become more and more configured, more and more filled with patterns that represent your history. This is why memories fade and become confused over time. The entropy increase continues. New memories overwrite old ones. Patterns degrade. What was once a sharp correlation becomes fuzzy. The details blur. You remember that something happened, but not exactly what, not exactly when. The entropy of the memory system increases, and information is lost to thermal noise. If the universe were running backward, if entropy were decreasing toward the past, this process wouldn't work. The thermodynamic arrow determines the direction of the epistemic arrow. Consider what it would mean to remember the future. To have a memory of tomorrow, there would need to be a correlation in your brain now with a state of the world that hasn't happened yet. How could that correlation form? The future state doesn't exist yet to correlate with. The information isn't there to encode. You can anticipate the future, of course. You can form predictions, expectations, plans. But these are different from memories. They're mental models, simulations, extrapolations from the past. They're not direct traces of actual events, and importantly, they're often wrong. Your prediction about tomorrow might be completely off, but your memory of yesterday, while imperfect, is a genuine record of something that actually happened. This asymmetry between memory and anticipation is profound. It shapes our entire experience of time. The past feels solid, fixed, determined. It happened. You were there. You remember. The future feels open, uncertain, yet to be decided. It hasn't happened yet. You can influence it. You can make choices. Here's a thought experiment. Imagine a universe where entropy decreased toward the future instead of increasing. Inhabitants of such a universe would remember the future and anticipate the past. They would experience time flowing backward from our perspective, but from their own perspective, they would still feel like time flows forward, because forward would be defined as the direction they remember from, which would be what we call the future. This shows that the arrow of time is not absolute. It's relative to the entropy gradient. Whichever direction entropy increases, that's the direction that feels like the future. The direction of memory formation, the direction of causation, the direction of time's flow. But here's the thing. We can't just reverse the entropy gradient and expect everything to work the same way backward. The very possibility of complex structures like brains depends on entropy increasing. Memory, consciousness, life itself requires being far from thermal equilibrium in a state where entropy can increase through metabolic processes. In a universe at maximum entropy, in thermal equilibrium, there would be no brains, no memories, no consciousness, no structure, no complexity, no information processing. So the psychological arrow depends utterly on the thermodynamic arrow, and both depend on the cosmological arrow, the fact that the universe started in a low entropy state and has been evolving toward higher entropy ever since. This brings up deep questions about consciousness itself. Is there something it's like to be a thermodynamic process moving toward higher entropy? Is subjective experience fundamentally tied to the arrow of time? Could a conscious being exist in a universe at thermal equilibrium? Or does consciousness require the flow from past to future, the accumulation of memories, the sense of temporal passage? We don't have definitive answers to these questions. The relationship between consciousness and physics remains mysterious. But what's clear is that our mental life, our sense of self, our experience of time as a flow from past through present to future is profoundly shaped by thermodynamics. This is related to a concept called the asymmetry of records. We find fossils, ancient footprints, photographs, historical documents. These are records of past events, embedded in the present. We don't find records of future events. No photograph of tomorrow exists today. No fossil from next year can be discovered. Why? Because records are low entropy configurations that carry information. A fossil is a very specific arrangement of minerals that preserves the shape of an ancient organism. Creating such a record requires starting from an even lower entropy state, and the process of record formation increases total entropy. Think about a photograph. When you take a picture, photons from the scene interact with chemicals in the film or sensors in a digital camera. This interaction creates a pattern, a record of the light distribution at that moment. The process is irreversible in the thermodynamic sense. You can't uncapture a photograph, can't make the photons uninteract with the film and return everything to its prior state. The past hypothesis, the idea that the universe began in a low entropy state, explains why records exist at all. If the universe had started at high entropy, there would be no structure, no order, no possibility of records forming. The fact that we have memories and records is evidence for a low entropy past. But let's think about volition. You can choose what to have for dinner tomorrow, but you can't change what you had for dinner yesterday. This asymmetry is so fundamental to human experience that it shapes our entire concept of agency and free will. Why this asymmetry? Again, it comes down to thermodynamics and causation. When you make a choice, when you decide to act, you're causing something to happen in the future. Causation means creating correlations between your action now and states of the world later. This creation of correlations is an entropy increasing process. Your decision to eat pasta tomorrow causes a chain of events. You go to the store, you buy pasta, you cook it, you eat it. Energy is expended, heat is generated. The correlations between your intention and the outcome grow stronger. You can't cause the past because the correlations with the past already exist. The past is fixed by the records that already exist of it. To change the past, you'd have to destroy those records, uncorrelate your current state from past states. This is thermodynamically backward, running against the arrow. Imagine trying to uncook pasta. You'd need to take the soft, cooked noodles and somehow reassemble them into hard, dry pasta. You'd need to remove the water that was absorbed, reconcentrate the starches, restore the chemical bonds that were broken during cooking. Each of these steps would require decreasing entropy locally while increasing it massively elsewhere. It's technically not forbidden, but it's so overwhelmingly improbable that it never happens. So the feeling that the future is open and the past is fixed is not just psychological. It reflects the thermodynamic structure of the universe. The future is the direction in which new correlations are being created, entropy is increasing, and the universe is evolving from its low entropy beginning. The past is closed because it's already been created, already recorded in countless ways throughout the universe. Every particle, every photon, every ripple in space-time carries traces of the past. You can't erase all those traces. You can't make the universe forget. This connects to how we think about free will. When you make a choice, you feel like you're creating something new, opening one possible future while closing others. And in a sense, you are. Your choice determines which correlations form, but this only makes sense in the context of increasing entropy. If entropy were decreasing, if the future had lower entropy than the present, you couldn't create new correlations pointing forward. The thermodynamic structure wouldn't support it. So our experience of agency, of being able to affect the future, but not the past, is grounded in the same thermodynamic asymmetry that explains why we remember backward and not forward. It's all the arrow of entropy manifesting in our mental life. This connection between mind and thermodynamics raises profound questions. Is consciousness itself an arrow? Does subjective experience require the passage of time in a particular direction? Some philosophers argue yes. They say the sense of time flowing, of now moving from past to future, is fundamental to consciousness. Without the arrow, there would be no flow, no narrative of experience, perhaps no consciousness at all. Others are skeptical. They suggest our experience of time's passage might be an illusion, a story the brain tells itself. The real world, according to relativity, is a four-dimensional space-time where past, present, and future all exist equally. The flow is just our way of processing this static structure. I don't think we have a definitive answer, but what's clear is that our mental life is profoundly shaped by the thermodynamic arrow. Our memories point to the past because that's the direction of lower entropy. Our planning points to the future because that's the direction of higher entropy. Our sense of self as a continuous being persisting through time depends on the accumulation of memories, which depends on entropy increase. In a universe at thermal equilibrium, with no thermodynamic arrow, there would be no psychological arrow. There would be no memories forming, no records accumulating, no distinction between past and future. And there would probably be no consciousness at all, at least not consciousness as we know it. We are, in a deep sense, children of the arrow. Our minds exist because the universe is far from equilibrium, because entropy is increasing, because we live in the flow from a special low-entropy past toward an inevitable high-entropy future. This brings us full circle to the biggest mystery of all. We've explained why entropy increases, why processes are irreversible, why memories point backward, but we haven't explained why the universe started with low entropy in the first place. That's the ultimate question, and it's one of the deepest unsolved problems in all of science. The ultimate mystery. Why low entropy in the past? Everything we've discussed, the second law, the arrow of time, the irreversibility of everyday processes, the direction of memory, all of it depends on one brute fact. The universe began in a low entropy state. About 13.8 billion years ago, the universe emerged from a hot, dense state we call the Big Bang. At that moment, or shortly thereafter, the universe was in a condition of remarkably low entropy. Matter and energy were distributed with surprising uniformity. The cosmic microwave background radiation, the afterglow of the Big Bang, shows temperature variations of only about 1 part in 100,000. This uniformity seems like high entropy, everything smoothly distributed, but in the context of gravity, it's actually very low entropy. Gravity is a force that wants to clump things together. A uniform distribution of matter has far lower gravitational entropy than a clump distribution with stars, black holes, and cosmic voids. As the universe evolved, gravity pulled matter together. Structure formed. First density fluctuations, then gas clouds, then stars, then galaxies. Locally, this looks like order emerging from disorder. But globally, gravitational entropy was increasing. The universe was evolving toward higher entropy states. The process continues today. Stars are burning, converting nuclear energy into heat and light, increasing entropy. Black holes are forming, swallowing matter, and maximizing entropy. The universe is expanding, diluting matter and energy. Everything is moving toward higher entropy. In the far future, physicists calculate it could take perhaps 10 to the 100th years from now before the universe reaches a state of maximum entropy. All stars will have burned out, all matter will have decayed or fallen into black holes. The black holes themselves will evaporate via Hawking radiation. What remains will be a cold, dark, dilute sea of photons and perhaps a few particles, all at nearly uniform temperature. No arrow of time because there's no entropy gradient left. But why wasn't the universe always in that state? Why did it start with low entropy? Why was there an arrow at all? This is called the past hypothesis, the assumption that the early universe had very low entropy. It's not really a hypothesis in the sense of something we can test. It's more like an initial condition we observe. But the question remains, why that initial condition? One answer is the anthropic principle. We observe low entropy in our past because only in a low entropy universe can complex structures like stars, planets, and living beings exist. If the universe had started at maximum entropy, we wouldn't be here to ask the question. It explains why we observe what we observe, but not why the universe is the way it is. Another approach invokes cosmic inflation, a period in the very early universe when space expanded exponentially fast. Inflation can explain why the universe is so uniform, but it doesn't fully explain why the pre-inflation state had low entropy. It pushes the question back but doesn't eliminate it. Some theories propose that the Big Bang wasn't the beginning, but a transition from a previous state. Maybe the universe is cyclic, going through repeated phases of expansion and contraction. Maybe our Big Bang was a fluctuation in some larger multiverse structure. Roger Penrose has proposed conformal cyclic cosmology, where the universe goes through infinite cycles, each beginning with a low entropy Big Bang. In his model, the heat death at the end of one cycle becomes the Big Bang of the next. It's an ingenious idea, but it's controversial and lacks strong evidence. The truth is, we don't know why the universe started with low entropy. Some physicists think the answer will come from a quantum theory of gravity, a framework that unifies general relativity and quantum mechanics. In such a theory, The notion of initial conditions might not make sense in the usual way. The Big Bang might emerge from quantum processes that don't require special fine-tuning. Others think we need to rethink what we mean by entropy in a cosmological context. Maybe there's a maximum entropy for the universe that's different from what we calculate. What's clear is that the arrow of time is not a fundamental feature of the laws of physics. It's a feature of the boundary conditions, of how the universe happened to start. In a different universe with different initial conditions, there might be no arrow, or the arrow might point in multiple directions in different regions. This makes the arrow contingent, not necessary, and that's actually quite profound. It means time's directionality is an accident of cosmic history, not a logical necessity. The universe could have been otherwise. Yet here we are, in this particular universe, with this particular arrow, flowing from a special, low-entropy past toward an inevitable high-entropy future. And it's that arrow that makes everything interesting possible. Stars, chemistry, life, thought, experience, wonder. The low-entropy beginning is the gift that allows complexity. Without it, the universe would be a featureless soup. Nothing happening, nothing changing, no one there to notice. With it, we get 13.8 billion years of cosmic evolution, the emergence of structure and pattern, the development of entities complex enough to contemplate their own existence. We are the universe's way of noticing itself, and we can do that only because the universe is out of equilibrium, riding the arrow from its improbable beginning toward its inevitable end. We exist in the middle of the story, in the interesting part. How long will this last? For life in general, perhaps trillions of years, as the longest-lived stars continue to burn. For structure in the universe, physicists estimate maybe 10 to the 100th years before even the black holes evaporate. These are unimaginably long times by human standards, but they're finite. The arrow will eventually run its course. Entropy will maximize. The universe will reach equilibrium. And then, in some sense, time will stop having a direction. But that's the far future. So remote, it's almost abstract. Here, now, we live in time's flow, carried along by the arrow, shaped by it, defined by it. Let's appreciate that while we explore what it means, living in time's river. We've journeyed through thermodynamics and particle physics, through cosmology and consciousness. We've asked why time flows forward, why eggs don't unbreak, whether you might be a random brain in space, and why you remember yesterday but not tomorrow. Let's bring it all together. Time has an arrow because the universe began in a special low-entropy state. Systems evolve toward higher entropy not because the laws forbid the reverse, but because high-entropy states vastly outnumber low-entropy states. The direction of increasing entropy defines what we mean by the future. This arrow manifests in countless ways. Broken cups stay broken. Mixed coffee stays mixed. Ice melts. Organisms age. Stars burn out. Every process we witness is consistent with entropy increase. The rare exceptions, local entropy decreases, like the formation of a snowflake or the growth of a tree, are always powered by larger entropy increases elsewhere. The universe as a whole inexorably moves toward disorder. At the microscopic level, the fundamental laws are time-symmetric, or nearly so. Classical mechanics, quantum mechanics, even general relativity don't distinguish between forward and backward in time. There's a small violation in the weak nuclear force, a subtle asymmetry in how certain particles decay, but this has nothing to do with everyday time's arrow. That emerges from statistics and initial conditions. The Boltzmann brain paradox teaches us that our low-entropy past must be genuine, not a fluctuation. If we were just a random fluctuation in an equilibrium universe, We'd almost certainly be isolated brains with false memories rather than evolved beings with real histories. The fact that we're not suggests the Big Bang was real, the low entropy was real. Gravity doesn't reverse time, but it shapes how entropy evolves on cosmic scales. Gravitational collapse increases entropy. Black holes are entropy maximizers. The expansion of the universe provides a cosmological arrow that aligns with the thermodynamic arrow, both pointing from the Big Bang toward heat death. Our minds are embedded in this flow. Memory formation is an entropy-increasing process. The psychological arrow aligns with the thermodynamic arrow because our brains are physical systems subject to the second law. We remember the past because that's the direction of lower entropy, where records and correlations already exist. We can't remember the future because it's the direction of higher entropy, where correlations haven't yet formed. All of this depends on the mystery of why the universe started with low entropy. We don't have a complete answer. It's one of the deepest open questions in physics. But the fact remains. We find ourselves in a universe far from equilibrium, with a past that was even further from equilibrium, and that makes all the difference. Think about what this means for existence. The arrow of time isn't just an abstract concept. It's the foundation of change, of causation, of narrative, of life itself. Without the arrow, there would be no evolution, no growth, no decay, no stories unfolding. The universe would be static, frozen, or eternally chaotic with no structure. The arrow creates the possibility of history. Events accumulate. The future emerges from the present. There's a direction to existence, a flow, a becoming. We are creatures of time, shaped by it, living in its current. Our very consciousness seems to be a pattern of organization that exists only in the flow. We are low-entropy structures, maintaining ourselves temporarily against the tide of disorder by consuming energy from our environment. We are eddies in the stream of entropy increase, complex patterns that persist for a moment before dissolving. And yet, what a moment! What a privilege to exist in this narrow window of cosmic history, this epoch when the universe is interesting, when stars shine and life evolves and minds contemplate the nature of time itself. The universe is about 13.8 billion years old. The longest-lived stars will burn for trillions of years. We exist in the early chapters of the cosmic story in a time when the arrow of time has not yet exhausted itself, when there's still plenty of entropy gradient to drive interesting processes. One day, in the inconceivably distant future, the universe will reach equilibrium. Entropy will maximize. Nothing will happen anymore because there will be no entropy gradient to power change. Time will lose its arrow. But that day is so far in the future that it's almost meaningless to contemplate. Here, now, we ride the arrow. We live in time's river, flowing from the special low-entropy past toward the inevitable high-entropy future. We are temporary, contingent, improbable. We are patterns in the flow, complex enough to notice the flow itself. The broken cup doesn't unbreak, because the universe began in a very special state and has been flowing toward equilibrium ever since. You remember yesterday because forming that memory increased entropy, and there's no thermodynamic path from the present to higher entropy in the past. Time flows forward because that's the direction that entropy increases, and entropy increases because the universe started with low entropy, and why it started that way remains one of the great mysteries. But the mystery doesn't diminish the wonder. If anything, it enhances it. We live in a universe with an arrow, a direction, a story. We are part of that story, riding the current from past to future, from order toward disorder, from the Big Bang toward heat death. And somewhere in the middle of that journey, we pause to wonder why time flows as it does, why eggs break and don't unbreak, why we remember and don't pre-remember. We are the universe asking itself questions about its own nature. We are entropy-driven patterns, complex enough to contemplate entropy itself. What a strange and beautiful accident we are. As you drift towards sleep tonight, let these thoughts settle in your mind. Time flows forward, entropy increases, the arrow points from past to future, and you flow with it, moment by moment, memory by memory, heartbeat by heartbeat. The cup breaks, the coffee mixes, ice melts, stars burn, you age, all of it flowing in one direction, the direction of increasing entropy, the direction from the special low entropy beginning toward the inevitable high entropy end. We can't reverse time. We can't unbreak the egg. We can't unmix the cream from the coffee. But we can marvel at the fact that we exist in a universe where these things happen, where time has a direction, where entropy's arrow creates the possibility of structure, complexity, life, and thought. We are children of the arrow, living in its flow, shaped by its direction. If this journey through time's mysteries has resonated with you, if you've found yourself wondering about entropy and consciousness and the deep structure of the universe, I'd be grateful if you'd consider liking this video. And if you'd like more explorations into the profound questions that physics and cosmology raise, subscribe to the channel. Your support allows me to keep creating these long-form meditations on the nature of reality. Until next time, rest well in time's river. Let yourself flow from this moment to the next, from waking toward sleep, from now toward tomorrow. The arrow carries us all, and there's a strange peace in accepting that flow. The universe began with low entropy. It will end with high entropy, and in between, briefly, beautifully, improbably, there is you. There is consciousness. There is wonder. There is the capacity to ask why time flows forward and to glimpse, however partially, the answer. Sleep well, fellow traveler in time. The arrow points forward, and we ride it together into whatever comes next.